Hello students, in this video we'll prove the Fourier inversion formula. So we're going to begin this by recalling the following fact. We know previously that if we look at the Fourier transform of e to the negative pi x squared, this function will Fourier transform to e to the negative pi xc squared, right? Now let's use our dilation rule. Our dilation rule says that if we look at a function f of delta of x, this will Fourier transform to 1 over delta f hat of xc over delta. So that's a localization property. So I'm going to combine these two results to prove the following. So if we combine these two results, we can therefore say that the function, let's now consider 1 over delta, 1 over root delta, 1 over root delta, e to the negative pi x squared over delta. Then what would it be for this function over here? So if this is my function over here, g of x, so this is my g of x, then what is this? This is exactly just 1 over the square root of delta, and then g of x over root delta, g of x over square root delta, like that, okay? And so now what happens over here, so I Fourier transform this function, what's going to happen? So by the Fourier transform rule, what will this transform to? This will Fourier transform to the following. It's the 1 over delta stays out in front by linearity, 1 over delta by linearity. And I'm going to have g hat of, then I'm going to have have to do the reciprocal, so that 1 over delta comes out by the reciprocal scaling law. And then I'm going to have a g hat of the square root of delta times xc, like that. So I just flip and I pull it out, okay? That's the scaling law. So of course those deltas cancel out over here, and this becomes g hat of root delta xc, which is going to be e to the negative delta xc squared. So this function over here is going to Fourier transform, therefore this Fourier transforms to e to the negative pi delta xc. Okay, excellent. All right, and that's going to be important. That's going to be an important result in our Fourier inversion formula over here. So that's one important result we have over here. And furthermore, we know a couple things about this function over here. So this function. So now let's consider this family of functions. If I consider the family of functions phi delta of x, which is 1 over the square root of delta, e to the negative pi x squared over delta, then we can see that this function, this family function satisfies 3 properties. The first property it satisfies that the integral over r of phi, of course these functions are non-negative, right? These are always greater than or equal to 0, which is one important property. X dx, they all integrate to 1. If I simply just use the fact that this function over here, e to the negative pi x squared, integrates to 1, this is, I'm just basically rescaling it and getting the same result over here because I have the same sort of scaling law in the chain rule, okay? And furthermore, that we know that the L1 norms of these functions are bounded. So in other words, that's just a direct consequence of this and the non-negativity. The L1 norms of these functions are bounded, like so. And finally, for any 3, I know that the integral over the points x that are bigger than or equal to epsilon of this family over here, phi delta of x dx, this tends to 0 as delta goes to 0. As delta goes to 0, this tends to 0 for all epsilon greater than 0. Okay, so for all epsilon greater than 0, this tends to 0. So in other words, this family over here forms an approximation to the identity. So in other words, this phi delta, this family over here is an approximation to the identity. And that means for any sort of reasonable enough function, I know that f convolution phi delta of x is going to converge to f of x for any sort of reasonable function as delta goes to 0. So that's the result we have for approximations to the identity. And we're using this approximation to the identity to prove Fourier inversion, okay? The other, of course, fact that we can use is we can trivially verify this. So one other remark over here, so remark, is that it's always the case that if we integrate over r, f of x, g hat of x, dx, that for real value functions, I can just simply switch the order of the Fourier transform. That's easy to check just by Fubini's theorem. Okay, so I can flip the order of Fourier inversion. I'm going to use this fact over here, this Poincaré version over here. So in other words, if you think about this, I'm just going to have 2 integrals over here, and they're both going to have an e to the negative 2 pi I x xc in them, and so you can just flip from one to the other. Okay, that's the idea over here. So these are both double integrals, and you can pass the exponential from the f to the g and the g to the f, like that. Okay, excellent. So now, okay, let's just be given a function of the Schwartz class. So if f is sort of smooth enough, so for any reasonable f, We can just say Schwartz class. That's the primary class we're interested in. That would be good enough, right? And of course, we can extend this too. For any sufficiently smooth f, what can we say? Well, if I look at the integral over r of f of x with these functions over here, with 1 over the square root of delta e to the negative x pi x squared over delta dx, I know that since this is an approximation to identity, this converges to, as delta goes to 0, this converges to f of 0, okay? But now by this passing the Fourier transform, this thing is the Fourier transform of what? This function over here, if I Fourier transform it, this comes with the Fourier transform of e to the negative g delta xc. So what this is over here is I pass the Fourier transform from one to the other, right? Just by the scaling, I can do the opposite translation too, right? So I can say, therefore, that this is equal to what? So in other words, I have the Fourier transform on this function now. I'm going to pass the Fourier transform on to the other function f, and then I'm going to have what function over here? So this is going to be the Fourier transform f of xc times what? Times this, the Fourier transform of that thing over there, which is e to the negative pi delta xc squared dxc. Okay, excellent. So of course here, now the Fourier transform is over here, and over here the Fourier transform is over here. So I just pass the Fourier transform from one function to the other using this remark over here. And now what happens as delta goes to 0 over here? As delta goes to 0 over here, since f is sufficiently, f is integrable, I can pass the limit into the integral over here, and this becomes just the integral over r of f hat dxc, right? So in other words, what we've just shown is we've just shown that f of 0 is equal to the integral over r of the Fourier transform. Excellent, that's one thing we need to know. And now what we're going to do is we're going to construct an auxiliary function. So here's the auxiliary function we're going to construct. Let's let f capital of, let's say f capital of y be little f of x plus y, the function that we're considering over here. Then what's the Fourier transform of this function f of y? So f hat of xc is the integral over r of f of y e to the minus 2 pi I y xc dy. Now, of course, this is really what? This is really x plus, this is the integral over here of little f, so this is really f integral over r of f of x plus y e to the negative 2 pi I y xc. Now we can change variables over here, right? How am I going to change variables? I'm going to let this thing over here be my u, so that's going to be my u. And of course I have a dy over here, so dy is going to be du since x is fixed over here, and this is going to turn into the integral over r of just f of u, e to the minus 2 pi I, and then y is really u minus x du. So in other words, this is just the Fourier transform of f. This is just f hat of, and there's xc, of course, xc, f hat of xc times e to the 2 pi I x xc. Great, okay, that's an important fact over there. And so now what are we going to do? So now we can conclude this. So now, therefore, what can I say? I can say that f of 0, so f of x, which is f capital of 0, is, now f capital of 0 is the integral over r of its Fourier transform, f hat of xc dxc, by this result over here. And now we know that that's exactly equal to this expression over here. So this is going to be the integral over r of f of x hat. So we're going to put an xc now. So let's put an xc. We can use x, but just be consistent. xc e to the 2 pi I x xc dxc, and that's a Fourier transform over there, right? So in other words, what have we just shown over here? We've just shown that f of x is equal to what? Is equal to the integral over r of f hat, its Fourier transform, e to the 2 pi I x xc. So whereas the Fourier transform had a negative sign over here, when you do Fourier inversion, you put a what? You have a positive sign on the integral over here. So the function can be recovered from its Fourier transform by integrating the Fourier transform against e to the positive 2 pi I x xc. Thank you very much.